Hello, everyone, and thank you for attending this talk. Uh, Today's topic is about demystifying the OpenJ9 JIT Inliner, which unfortunately is not an easy thing to do, but I'm going to try my best. So the objective of this talk is sort of cover some high-level key components of the OpenJ9 JIT Inliner. And then we're going to try to use that understanding to navigate our way through some trace inlining output and diagnose some inliner issues. Overview of this talk would be first of all some introduction to the concept of inlining as a compiler optimization. And then we'll go over the high-level overview of the OpenJ9 inliner. And then we're going to talk about some of the inliner phases and some heuristics involved. And then we'll start looking at the inliner logs and diagnosing inliner issues and look at ways that the behavior of the inliner can be controlled. So first of all, what is inlining? So it is the optimization that's responsible for replacing calls to other methods with the body of the call methods. And what that does is essentially reduces the overhead of method invocations, the control going out of one method to the other. And it also unlocks optimization opportunities. Inlining does increase the size and complexity of the method being compiled. So you're going to see more of a compilation resource usage. But then ideally, it does result in better runtime performance. And one thing to keep in mind is that not all inlining is beneficial to the same degree. And therefore, we need heuristics that will determine the most ideal way to use inlining budget. So let's look at a very, very simple inlining example. Imagine you have a car that has some fake program get blinker fluid usage. And it's always going to return the same thing. But when you're compiling get blinker fluid usage, you just have the context of that method itself. You don't know what compute usage does. You do know that you're passing start val and end val to that function. And what compute usage does is it just does some, I guess, there's a conditional and then there is an arithmetic. So with inlining, what will happen is that the call to compute usage would, I guess we can imagine it as being replaced by the body of compute usage. And then now that we have the body of compute usage, we know what start val and end val is, so we can start replacing the different variables with the actual constants that are there. And that's only possible because we know what's inside compute usage. Now it's part of the same compilation scope. And then, we can fold away all of these different operations, and eventually this whole function just becomes return 80. So that's basically the gist of it. And we'll look at a more complicated example later on using the OpenJ9 inliner. So the OpenJ9 inliner runs in all non-code optimization level compilations. And there is a greater level of inlining budget available at higher up levels. So code optimizations use trivial inliner. And what that does is just only handles the most basic and small methods that you can imagine. Like even anything that does more than a few operations would disqualify from code optimization inliner. So we're gonna mainly look at the inlining behavior at level 1 and above. So inliner forms its own standalone phase during compilation, but then there's also a way to make use of the inliner as part of other optimizations, because other optimizations may unlock further opportunities to inline things And you can see that example with how value propagation does it, or escape analysis, and a few others. So let's look at the structure of how the inliner is implemented. So we have tr_inliner base that contains the common functionality, and then there are implementations of it such as tr_inliner, and then there's tr_ multiple call target inliner. Demystifying provides a very simple inlining functionality that's used by tr_inline call class. That's part of the usage of inliner as an API that other optimizations use. And then multiple call target inliner is the implementation that's used by OpenJ9, and that's going to be the focus of this presentation. So here are the various places that these classes are implemented in. It's not really organized in the most straightforward way, but if you wanted to look at multiple call target inliner implementation, you'll find most of it in inliner temp for J9.cpp, for example. So here's an overview of the various inlining phases. As inliner is an optimization, it has a perform function, and what that does is it calls perform inlining, and perform inlining then would call inline call targets, and then we'll go into other details about that, but you can see that all of this functionality can either be implemented in tr_inliner base or tr_multiple call target inliner. There are various reasons why. To see what happens during inliner, so inline call targets, when it's called, what it'll do is the top level method, which is a method in compiled, is going to walk the trees and then look and then find the call sites. And for each call site, get symbol, find inline targets. And then for all the targets that are found, there will be an initial size threshold check. And then once it passes that, it is going to go to wait call site, which makes use of estimate call size. And then it's going to iterate through the call targets and remove calls that hit size limits and node count limits. By the way, we could also get the calls eliminated during the earlier steps in this process. And then sometimes we have to override all of that. And, there are some methods that even if our heuristics determine that it should be in line, we override that anyway. So there are some methods that are considered always worth inlining. So that's what will be done after all of that. And then the final transformation phase begins through inline call target method. So here are some definitions that I think are important to keep in mind. So the size is the estimated size obtained mainly by analyzing bytecodes of a method and all of its callees that may get inlined. And it is done through recursively going down different call chains. And the weight of a call site is the final value that is assigned to it based on various factors, mainly the call frequency. And what that does is it determines the amount of inlining budget that is consumed by inlining the call. Call sites, they represent like an actual call that you see in the IL, and it bundles various information that are relevant to that specific call. And call target is like an actual method implementation that may be a possible inline candidate. And a call can have multiple call targets, and For example, when we have virtual methods that can have overrides, but only one would get inlined, even though the name of the inliner implementation is multiple call target inliner. We actually only ever inline a single target. There is reasonable amount of support to inline multiple call targets, but at this time, it is not in a 100% ready state to provide enough of a benefit to turn that on by default. Okay, so we spoke about wait call site and the importance of that. So because the amount of inlining budget that is consumed by a call site that is being inlined would depend on the weight that is assigned to it. So the lower the weight of the call site, the more likely it is to get inlined. What wait call site does is it starts with a value that is returned by estimate both sides. And then it has its own heuristics to determine whether to increase or decrease the size of, the weight of the call, and it is dependent on several factors, mainly the frequency. If we want to encourage the inlining of the call and not have that come in the way of being able to inline other calls in the method, then we should have heuristics that reduce the weight of that method and vice versa. So what this phase essentially does is that the more benefit we get out of inlining a certain call, the less, and especially if inlining that call would provide further optimization opportunities, the less inlining budget would be consumed by inlining. And now let's make some distinctions between wait call site and estimate call size. So estimate call size is called by wait call site. So wait call site is called once from the top level method for every single call site that is found at the top level method. And then estimate call size is called once by wait call site, and is using the value that is returned by estimate call size. And what estimate call size does is it recursively analyzes along chains of calls, and it starts from the top level method, and then it goes down all the way to how much the size threshold would allow, or until we reach a maximum call depth, so that we don't, for recursive calls, for example, we don't want to keep going down that level. So estimate call size's role is a lot broader than what its name might suggest. It obtains the size of a call graph by analyzing the bytecodes, and then it also does some minor adjustments to the size estimate based on various factors. It's based on the degree of benefit to inlining. ECS would terminate along call graphs once the size threshold is hit. And the threshold amount is determined by the op level. So the higher op level it is, the larger analysis we're willing to do, because we would have more of an inlining budget. And then ECS also constructs a control flow graph from the bytecodes, and it obtains call size along the call graphs, propagating argument info from one level of the call to another. And it also can generate IL during this analysis, and call that peaking IL. And sometimes that becomes necessary to propagate object info from one level of call to the other. And unfortunately, at this time, all of the peaking IL and the CFG that are generated has to get discarded at the end of this. Estimate call size also makes use of an inverted emulator to obtain the call size from bytecodes. An interpreter emulator, as the name suggests, is like an interpreter that has like an operand stack, and you can iterate with or without state and with state. It does push and pop into the operand stack, and sometimes that becomes necessary. For example, when you're trying to compute when you're trying to find a call target that depends on some earlier operations that could either be some load from a field or some return value of a function. Yeah, so basically, interpreter emulator is a much cheaper way to propagate object information along call graphs compared to generating IL, and is intended to eventually remove the need for generating IL during ACS. So let's briefly just go over some another concept that's important to inlining, which is inlining guards. So just because a method is inline doesn't mean that we are always going to run that. Let's look at this example here. So we need to, so we can have two different implementations of method one based on whether the type of A is class A or class B. What we need to do is that we need to make sure that if we inline whatever we inline matches the type that is passed to this method at runtime. So what we rely on is some profiling information. So based on the version of method one that is called, there will be a frequency assigned to it, anything from 0 to 1. If let's say A dot method one is the inline target, due to the target having a higher profile frequency, a guard will be inserted to ensure that the inline code is used only when small a is of type capital A. There is I guess a bundling struct that covers that, which is TR for virtual guard selection, and it contains information about the guard kind and the guard type of a call target, and that instructs the inliner to generate the right kind of IO to insert that runtime check. So for this example, the guard kind would be TR profile guard, and that comes from the fact that whatever decision has been made was through profiling information. We assumed we inlined based on whatever was the more frequently taken path between method one of A and method one of B, and then if there is a mismatch at runtime with the passed in type, then we're going to bypass the inline body and go through like a regular virtual call to A dot method one. So there are a few other guards that I'm not going to go into too much, such as HCR guard and OSR guards, because what I was hoping to do in this is to sort of go through an exercise, and here it is. So this is a method from one BRC. I think it's a series of solutions to, I guess, do some operations in the most efficient manner. And this is one of the parts of one of the solutions where we came across this hash function showing up a lot in the profile, along with some of the methods here. that we would like to get inlined. So after, let's say, profiling analysis and everything, we found that it is essential that all of these memory segment.get operations get inlined. Integer.rotate left doesn't need to get inlined because it is an intrinsic function that's handled after inlining, and therefore there will be no benefit at all to inlining this. So here, let's just look at one of the memory segment.get operations and see what's underneath. Just at the top. So here's the memory segment.get method that we see, and it is a bit of a mess, but I'll try to simplify it. It's basically there is a whole bunch of methods here, and you can sort of understand the caller and callee relationships based on the level of indentation. Let's try to highlight the most important parts of this call graph, which is, for simplicity, we're just going to ignore the other things that are mostly just various checks. So with that simplified call graph, we now have this, and the reason why we want to look at this is because we need to inline down to this unsafe call to get the performance benefits we want. So all memory segment.get operations use unsafe operations underneath, and it requires inlining all the way down to the unsafe operation for better performance. And that's because we are able to transform these unsafe operations into simple loads and stores. So all of this stuff that we just saw eventually ends up being just a simple load or store. And the third and the fourth memory segment.get calls is a different type, which involves readings into some byte array. So that uses unsafe.get bytes. But the idea is pretty much the same here. Okay, so let's say that we were not getting any of those memory segment.get operations inline as we would like. So the first step would be to generate a trace full on a trace inlining log to see what might be happening. So what are the inliner logs? So the JIT option, so notice that I have both traceful and trace inlining in there. Traceful just briefly touches upon what happens during inlining, but it doesn't provide the full heuristic trace of the inliner. You have to use trace inlining to understand the decisions made in the inliner and debug inliner if you want even more detail. I'm sure in many of your experience, but trace inlining output can be quite overwhelming. But let me assure you that it does get easier to understand and work with once you understand the various inliner phases. And trace inlining output is meant to be read as a trace of all the places that the inliner has been, rather than trying to see it as a concise trace that is in a summarized form that is going to be of any use to you at all. So now let's, with the log that we just collected, let's try to see what the inlining outcome was. And the easiest way to check what got inlined is to check any of the call stack info tables after the inlining phase. So as you can see here, it's trees being listed after inlining. And here we have memory segment.get. Okay, so let me just go a little bit over the call stack info table. So it just lists all the callee methods that have been compiled in an easy to read format. And callee index is an ID that's assigned to every method that got inline. And it starts at 0 with 1 reserved for the top level method, which is like the root method that is being compiled. And yeah, so the index starts at 0. The caller index corresponds to the callee index of the caller method. So it can be useful in establishing the caller and callee relationships. And then we have the bytecode index. The bytecode index corresponds to the the bytecode index within the bytecodes of the caller method, which corresponds to this invocation. Okay, so let's go back to the log, and what we wanted to do. So our goal was to inline all of these 4 calls that are highlighted in red. But in the call stack info table, we only see 2 instances of that. Well, that's not what we're looking for, unfortunately. Why is there only 2 of them? What about the other 2? So an easy way to start figuring it out is to look at to search for a list of call graphs to be inlined within the inliner log, that summarizes all of the call graphs that were considered for inlining, along with the failure reasons right before the start of transformation phase. So here we see all of the 4 memory segment get operations being considered, and for the first 2, we see that they're inlineable targets, and then the second, and then the third and the fourth ones have exceeds bytecode threshold on them. So that's under the failure reasons. Inlining failure reasons help us quickly identify the cause behind excluding a method from getting inlined. Inlineable target, override inline target, and try to inline target are actually the success reasons, but based on where they're defined, they're classified as failure reasons as well. But those are actual success ones. So for methods that have that tag, they would get inline. So the failure code that corresponds to the failed inlining of memory segment or get was exceeds bytecode threshold. And this one is set when a call target exceeds the size during the initial exceed size threshold check. And that is performed prior to wait call size or estimate call size when we go to the initial set of callees at the top level. So there are many other failure reasons, each of them set by various parts of the inliner heuristics. So we have trim list of callees, and that happens when as you're once you get all of the inlining targets, and then you try to add up how much all of them, how much budget all of them would consume. It actually stops at the point where we exceed the budget, and the rest of the calls get assigned trim list of callees. So that's one reason. And then some of them are not compilable callees. So that's usually for when you have a native upward call, or anything that's that doesn't have a Java implementation, or something like that. And some of them can be explicitly excluded from inlining from certain hard-coded method lists that we have, or through command line options that you can define. And then sometimes it can have like a poly too many bytecodes, and that's usually set by estimate code size. And there are many other failure reasons. It's too many to cover here. Okay, so we need to check how the call target was handled earlier by checking the call target address. So you find the exact call target instance of interest. So when you're searching, you should exclude the leading zeros. We have some inconsistent formatting here. So let's look at the first instance of the failure, which is ending in 6E0. And when you search for that, you're going to see the two places of interest here. One is, the call target being created, and then there is an exit size threshold. So from here, you can see that the particle size that was estimated was 13. And then in exceed size threshold, the size suddenly becomes 260. So what exceeds size threshold does is it takes the frequency information of the block containing the call, and it can blow up the size of some call site because it thinks that it's not worth analyzing down this poly because it's not in a frequently taking enough path, and therefore it will exceed the size of 200. And you can also see what is being compared with that, which is method in a warm block bytecode size threshold, which is 200. And then you're going to see that this call target gets removed because it exceeds bytecode threshold. So the reason why we have this check in the first place is because it saves the ECS recursive walk from having to spend any significant amount of time trying to analyze call graphs in call blocks. But in our case, we benefit from memory segment.get operations, and therefore, we want to find ways to overcome that. So I'm sure many of you have done this. But yeah, you can control the inliner behavior, and you can control that at various phases. The key to being able to do the right thing is to know exactly what decision you're trying to override. So there are two ways. It's either command line options, and they can either be set for all methods or specific method compilations through option sets. And then there are also environment variables that are mainly intended for experimenting and fine-tuning, and that will alter inliner behavior globally. Globally meaning for all compilations, not just the methods you're trying to look at. So there are two ways we can get past the exceeds bytecode threshold issue, preventing the inlining of the method we want. So we can try using try to inline, and then the regex that would match that method. And then the other option is to raise the method in one block bytecode size threshold value to like 261, and that would be one more than what the limit we're trying to deal with here. Yeah, so there are other command line options too, and there's way too many to cover, which is why I'm not going to dive too deep into them. Using the knowledge here, we're going to just try to use the command line option, try to inline. So now we have the new command Java option set up here. So it's the same stuff, except we now have try to inline as an additional option being added. So the inlining outcome shows that, yeah, we do get all of the memory segment.get methods inlined here. And let's see what happened during exercise threshold check. So as you can see here, we do still have the same sort of situations, like bytecode size is 13, but it's low enough to 260. And then we see that, yeah, it does exceed the size threshold, but then try to inline pattern matched. So, we don't care about that. So skipping size check, and then the call targets, they would get assigned override inline target tag. So that is used to tag methods that have been set as a result of some override command. In our case, try to inline was the override condition. So now that we got that through, the other issue we have is the fact that we only get unsafe.get by stuff inline all the way down. But then for the other one, like the one that deals with integers, they terminate at a certain level. We don't get all the way down to the unsafe operation. So that's a problem because with this, we're not going to get any of the performance benefits we're looking for. So let's go back to the call graph for the second log that we just generated, and then we'll see that this is the level where there is some failure code assigned, probably too many bytecodes, even though everything under that, all of its callees are tagged as inline effect target. The outermost method that gets tagged as not inlineable is going to result in discarding all of the subsequent descendants of that caller. Okay. So bar handle segments as ins get marked probably too many bytecodes. So we need to overcome the failed inlining of bar handle segments as ins.get. And this probably too many bytecodes is usually set during estimate code size. So if we search for that target that got tagged that way, we would see that we're at the ECS level, and here ECS is, as you can see, the depths are changing from 5 to 4 to 3. So it's basically coming out of the recursive walks that are done. And at a certain point, this target gets set as a call graph too big, and therefore it gets removed. So now it's a little confusing here, and and the reason I wanted to show this example is because you often have to face this situation all the time. In this case, the confusing part is the fact that the size is 611, but then size threshold 2500, but somehow we're still, exceeding the size threshold. So this is one of the cases where you would have to look in the inliner code to understand the reasoning behind that decision that was made. What I did was search for, set one call graph too big, and so that revealed the part of the inliner where this decision was made, and we would find that during ECS, the estimated size cannot exceed big calling threshold, and that is done when when ECS is recursively going across different callees in the call graph analysis. There's a case of a very large method. We should discard that because that's going to be way too expensive based on the frequency or like the inlining budget that we have available. So based on the off level of the log you're looking at, you'll be able to determine how the big calling threshold is obtained. And in my case, it was com get options get big calling threshold, and I was an x86, so it was set as 500. So we can easily overcome this by including variable segment as ins.get into our inline. But let's just try something else this time. So let's try to alter the big calling threshold amount. In this command now, we set it at 900. So as you can see here, we did get all of our unsafe methods inline. All of the memory segment.get operations inline. So, we are in the ideal state, and you would no longer see any of these methods show up near the top of the profile as it did before. So Now, I guess, step 10 might also be the most important one. In this exercise, the inlining allowed, it reduced a set of very complex file graphs into what would mainly be simple load trees as unsafe operations get transformed by existing unsafe method handlers in the compiler. If we can clearly establish that always inlining memory segment.get methods and bar handle segments as in .get methods, if they provide a measurable performance improvement across several workloads, it may always be worth inlining these methods. So as these methods are JCL methods, one way could be to recognize them and have them be part of the always worth inlining methods. And that would result in having all of these heuristics all of these heuristics not affect these methods, and they would always get inlined. And that is actually currently the case. These methods do have force inline annotations. For this exercise, I had recognizing force inline annotations disabled so that we can sort of go through some of the process that was done here. Yeah, and then another thing you could do is improve the inliner itself. So over here, we saw that the inliner log had some information lacking in the trace inlining output, and that required us to go look for stuff in the inlining implementation, which is not ideal. It can be time consuming, especially for someone who is working on the inliner for the first time. So therefore, the other way you can improve the inliner is to improve the output we get in these trace inlining outputs. So, in this case, we could have improved the set one call graph to big output to also include the big poly threshold. So we would immediately know what to alter in order to get the desired outcome. So I'll just summarize with the brief message that I hope this presentation brought. A high-level understanding of the various inliner phases is useful for inliner problem determination. It might be tempting at first, but it's not really useful to attempt to read through the trace inlining outputs. It's not meant to be human readable or concise. There's always humans that are reading it. So instead, the right approach in most cases would be to figure out what you want to get inlined and then identify what failed to get inlined, and then identifying the failure reason, and then going to the trace inlining output to understand the decisions that have been made for that specific call target that failed to get inlined. And that, in most cases, should help you navigate through the problems you might see during inlining. So that sums up my presentation for today. And if you have any questions, please go ahead.
There was one question in the chat. I don't know, Jared, if you're still on, do you want to read your question or just state it, or should I just read it out?
Either one of us can read it. I don't care.
Go for it.
Are there any tooling available to analyze code to determine if something can be done to make it more inline friendly? Does Bob or WCA have functions similar to be able to do something like that to analyze Java code to make it more inline friendly?
I'm sorry, I don't think I understood the question. Would you be able to repeat that, please?
Is there any tooling available to make to basically analyze a method using AI, any of the AI tools we have?
Unfortunately, I haven't tried doing that yet, but it is something that definitely AI tooling would help us understand better. But that's not something I have experimented with yet.
I mean, even pre-AI existing tools.
No, not that I'm aware of. I don't think there are any tools that would automatically help you get clearer answers out of these inline logs.
Sorry, were you asking about AI tools to restructure your code to make it more inline friendly? Is that what the question was?
Remove the word AI from it, yes.
Tools, right, okay. Sorry, yeah, I just as opposed to helping a human read through the logs. Okay, yeah, I guess those are two different questions. I don't. So the question that I just asked, which I think is what Jared asked, I don't know if anyone on the call has any experience with using tools to help your code be more inliner friendly. Certainly, that's an OpenJ. You could sort of say that's an OpenJ9 statement, but I guess that's true in general anyway.
Yeah, general profiling to say, hey, if you did this, you would possibly get better performance because we'd be able to inline that.
Right. And in theory, that could be extended, sort of thinking, but that could be extended beyond the inliner, of course, as well, to just optimizations in general. Although the whole point of the optimizer is not to be, it should be sort of agnostic to what the user is doing, just do the best job it can. Anyway, yeah, I'm not sure if anyone else on the call has any experience with that.
Yeah, I mean, the reason I asked is there's reasons why we have failed to inline. And if there's things that we can do to make the code so it doesn't fail to inline because of certain defaults that are set within the JDK, that's a helpful thing to know to say, hey, if your code was structured this way, we would not fail to inline in that particular case. That's where that concept came from to help address what Devin just posted into the chat.
As a user, writing user code, if we fail to, so there is nothing specific you could do to, get something inline or not. It depends on, basically the inlining budget that's available and what information we would be able to profile running in the JVM. And the user at this time, if they do want to inline something, I guess like the OpenJ9 inliner heuristics would be the primary, I guess, decision maker in this. To override that, it's only I guess, I'm not sure if there has been cases of, force inline annotations, for example, being used in user code, but I don't think so. But in JCL code, at least, that's one way that the OpenJDK developers have been able to, I guess, force things getting in line because they believe that there is a lot of benefit in getting that done. But for user code, I don't think that's supported.
So as part of your diagnostic process, you mentioned that you should try to inline. So what exactly does that do under the covers? Because you think that the inline would already be trying to inline. So what does adding that option, how does that change the inliner's behavior? What is happening internally?
So the name of the option doesn't, it's not a good true reflection of what it tries to do. It's essentially what it's trying to do is like try to inline anyway, even if you determine that it cannot be inline. There are some cases where that's going to be impossible anyway. For example, it's the outer collar of that method, for example, doesn't get inline for other reasons, or there is some object info needed to find the right call target that is not available. So in those cases, like as long as it's possible to inline something, we would ignore heuristics and try to inline it anyway.
So even if it exceeded the bytecode threshold, you
Yes.
would still do it?
Yeah.
Okay. Right.
Any other questions?
I guess I've got one. So, are there any differences in the handling of between a force inlining annotation and try to inline? Will they do similar things, same things, similar things, or do they do different things? I guess. Or like, are there different? Well, I guess. Are there differences between how they handle things?
That is, so try to inline is more like an option that you provide as a, like, when you're executing the JVM. So that's something the user can define. But force inline is more of like hard-coded stuff that's within the inliner heuristics, as well as like in the JCL when they have a force inline annotation. They are treated, in similar ways, where like despite what the heuristics say, we're going to get that inline anyway. So force inline is more like, it's not the Java user is not able to affect that behavior. I mean, you can, I guess, if something is force inline, you can disable that using don't inline. But yeah, try inline, force inline would treat, if they have, for the most part, yeah, you can see it.
Will something annotated, will a method annotated with force inline always be inline?
Always been inline, except when we have a hard limit on the number of nodes that we can have. So that's, as far as I'm aware, that's when we would terminate. We have like a higher node limit in cases where we have method handles involved in there. So that's when there would be a greater amount of inlining is happening. But for most Java methods, there is a hard limit that we might face that always inlining is not going to really help. Otherwise, the entire compilation would fail due to running out of space and all that.
That kind of leads me back to something I was thinking earlier in your presentation. You were talking about peaking IO.
Yeah.
And how we will peak, and if once we've made some decision, we'll actually throw away the IO that we produce. Does that count toward the node count? Even
No,
if we throw it away?
It doesn't.
Reset them, but it's not okay.
Node count is done at the end of ECS, towards the end, just before transformation. That's when we would be handling, the budget consumption.
Okay. Yeah.
If there is no other questions, thanks everyone for attending this talk, and yeah, you can always message me if you have any further questions. Yeah, I'll stop sharing.
Great. Thanks, Nizzy. Thanks, everyone.